All right. Get graphing. I was only showing on one. Both. Might have just. Okay, I guess the other one. TBD. What? Uh, okay, that might do it. Turn each one on individually. That's the trick. Good to know. Want to ask something? It's hitting up the chat. Hey, hi. Yes, you can come to in-person lecture if you desire. There's several people here at least. More than welcome. 20-ish, 30, 25, 25 to 30, I'd estimate. Make sure we're sharing. Don't want any more of those issues. Got us before. Okay. All right. What we got for today? Well, we're going to talk degrees. We're going to talk directed graphs and graphic sequences and this and that. A lot of stuff. All kinds of pages here we're going to get to. It's going to be exciting-ish. And so, would mention, you want to mention the existence of the quiz. If you weren't paying attention to your email, you should note that we're just going to keep the same thing we've been doing for the first couple of weeks. Pretty much just submitted on submitting. Still going to try and end Thursday class a little early so there's in class time for it. But, you know, yes, whatever. All right, so, you know, see what the questions are, be aware, because we're going to pretty much cover all of that today, except for this one. There's a proof that we've really already done, so hopefully that shouldn't be too much of a challenge. All right, more degrees, directed graphs, all kinds of stuff. So recall last class we talked a little bit about degrees, the degree sum formula, or the sum of the degrees in the graph is equal to 2 times m, where m is the cardinality edge set in the graph. So we're going to kind of go from there. We're going to extend that to directed graphs in a second after we start talking graphic sequences. Well, first let's define, we have before in the past, just as a refresher, a degree sequence. It's just a list of all degrees for all vertices in some graph. So if we have a graph here, it's one of those, the degree sequence. Occasionally we'll do them in sorted order, sometimes not, doesn't really matter. Degree sequence is just going to be a list of the degrees, so 1, 3, 2, and 2 would be the degrees that we have here. So we could just say 1, 2, 2, 3. There's our degree sequence, S of G. Degree sequence of graph G. 1, 2, 2, 3. Just a listing of all the degrees of all vertices. Kind of going one step farther, maybe one step back, who's to say? Graphic sequence. It's a list of, maybe it's a step sideways. I don't know. Essentially, like a degree sequence, a list, or a sequence, if you will, a list of degrees that can realize, that's a key term we'll define in a second. A, in this context, simple, undirected graph. Consider simple undirected graphs here, because this is going to be the more interesting problem. Arbitrarily, sequence can represent a loopy multigraph pretty arbitrarily, as long as the degrees sum to even. Leave that as an exercise to the reader after today. But so here, when we're talking graphic sequences, always consider simple undirected. This realized term. So that realized term, when we say, sequence can realize a graph, what we're saying is a graph can be drawn, can be constructed with, when I say graph here, again, simple undirected graph with a, vertex set of cardinality equal to kind of the cardinality of the set of the degrees in that sequence, where there's a bijection, a one-to-one mapping from the sequence to the degrees of the vertices of graph G. So if I just gave you three closed bracket, got those a little mixed up there. Good. So if I gave you that sequence, can a graph be constructed with those degrees? Yes, obviously. What is it doing? Obviously, we can construct a graph. And we would say S is graphic. So outside of explicitly instantiating the graph, I'm going to do that with trivial cases here. What about in general? What about an arbitrarily large sequence? There a way we can, determine not all sequences are going to be graphic. Or we would say consider call that S1, this S2. S2 we can definitively say is not graphic. Why is that? So we've talked about the degree sum formula. For any graph, the sum of the degrees must be even. We sum up these degrees, it's quite definitively odd. 7, last time I checked, is an odd number. But simply having the sum of the degrees be equal. Sum of the degrees equal to an even number. That's a necessary condition, but it isn't a sufficient condition. Throw down a note there. Note. I'll say even degree sum. Necessary, but not I come up with a pretty trivial example here. Call it S3. Let's just say sequence cardinality 2, 10, and 12. We realize a simple undirected graph with two vertices. One of those vertices has a degree of 10. Those vertices has a degree of 12. Well, might be tough. Might be tough. I'd say here S3, not graphic. question, obviously. Mine is why. Their characterization. Characterization of sequences that we can say definitively are graphic. That kind of is. And so, how can we tell if such a sequence is graphic or not? So I'd like to introduce you to one of the big dogs of graph theory. Here we go. Always enjoy drawing one of the big dogs. Okay. This is actually one of my better ones, to be honest. Call this the big dog. GT. BDOG. BDOGT. Big dog's graph. What is that big dog? The Havel-Hakimi algorithm, or theorem / algorithm. So Havel-Hakimi. So basically, this theorem is characterization of sequences. Kinda, it's can be used in such a way, algorithmic fashion. Basically, consider sequence. S, we're going to say equals D1, D2, dot, 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 up to some D sub n, where D1, so it's a non-increasing sequence. In other words, degrees are sorted in reverse order, largest to smallest. So our sequence is considered sorted in that way. So that sequence S is graphic if and only if sequence S prime is graphic. Prime, where S prime equals 2 minus 1. This is a little confusing, I will say. 1 dot 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 to this D. 1 minus 1 dot 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 n is, all right, so this is confusing, but we'll work through some examples just because the notation feels a little wonky. There really isn't a better way to kind of show it. So the Havel-Hakimi theorem essentially considers sequence S, again, non-increasing order. That sequence is graphic if and only if some sequence S prime is graphic, where S prime is defined as D2 minus 1, D3 minus 1, up to some D sub, the original D sub 1 plus 1 minus 1, D sub n. So if S prime is graphic, then in fact, S is graphic. So let's work it out. Let's do an example here. I think that'll make things a bit more clear. We consider S to be equal to 3, 2, 2, 1. So we're going to say, see this sequence. So we don't know if this is graphic or not. Let's pretend we don't. And let's use it as several examples of a graphic sequence. Forget that. Just consider it as some arbitrary sequence that we want to evaluate. Well, we have our S. What is S prime? How is S prime defined? Well, essentially, we remove that original value, and then we decrement whatever the value is. We decrement 1 from the next, that value, number of integers in our sequence. So our S prime is defined as 1, 1, 0. So hypothetically, we don't know if that sequence is graphic. This is what I was kind of referring to when I said this algorithm, kind of an algorithmic approach. And essentially, we're iterating through our sequence, really, until one of two things happens. Until we end up with, sequence that is obviously graphic, or a sequence comprised of only zeros, which is obviously the graphic sequence of just an empty graph. Or we end up, say, potentially, imagine, well, we'll do some examples in a second, but here, just to finish up this example first, our S double prime would be 0, 0. Which is graphic. So because S double prime is graphic, S prime is graphic. Because S prime is graphic, S is graphic. That's what Havel-Hakimi is talking about here. We have our sequence S, non-increasing order. That sequence is graphic if and only if S prime. S prime is defined as second value, third value, fourth up to whatever the original D sub 1 value are all decremented by 1, and that first value is so we can iterate some number of times until we end up with either a sequence that is obviously graphic or one that is obviously not graphic. Yeah.
What does it say right?
What was that?
Third value. Like,
Yeah, it looks a little messy. So we're indexing essentially slightly more clear. It's not this. Maybe that's a little more clear. D sub 1 plus 1. So the D sub 1 plus 1 index in our original sequence.
That's index.
D sub n minus 1 up here. Indexing from 1 to n. Only, so here, let's consider D sub 1 equals 3. So we subtract D sub 2, D sub 3, D sub 4. The next three values in the sequence.
But there shouldn't be. -1. He's showing that there shouldn't be.
Yeah. So it's just the value of D sub 1, the next integers in the sequence, however many that is. Maybe this isn't the best example. I don't know. You can see going from S prime to S double prime, only decrement 1. So here, our D sub 4 is equivalent to D sub 1 plus 1, which equals just D, obviously 3 plus 1 equals D sub 4. So that would be the last value that we would decrement. Yeah.
So we're basically just taking the edges from the biggest node and subtracting them out across the rest of the nodes.
That is exactly what we're doing. We can algorithmically realize a sequence by essentially just doing that. Yeah, so let's just do that now and we'll work maybe one or two other examples. So given so we can realize a graph explicitly in that sequence. So, or given a sequence, we can realize some graph. So that graph that we realize, I mean, so it's not going to be necessarily a unique graph of a given sequence. There could be, arbitrarily large number of graphs realized from a given sequence. That could all have the same, degree sequence. Like, I mean, quick example here. And if S equals 2, 2, 2, 2, I guess we need more 2 and 2, 2 and 2. We could have a cycle of length 6 or 2 cycles of length 3. In other words, I mean, the graph, there isn't a unique mapping sequence to graph is the point that I'm making here. So a given degree sequence can realize an arbitrarily large number of possible graphs. I mean, maybe not arbitrarily large, but depending on the length of the sequence. Some combinatorially large number of realizable graphs, which actually explodes quite readily, more so than this whole realization problem is actually, pretty. There's a lot of tricks there. Okay, so if we wanted to realize a graph of a given sequence, we can do as is suggested, or essentially we consider every time we remove a degree and decrement the next, d sub I values in the sequence, we're effectively just constructing edges from that, vertex represented by that d sub 1 to each of the vertices represented by d sub 2, d sub 3, d sub 4, etc. So we can map each value in the sequence to a vertex. And we draw an edge. I'll just say it's d sub I, d sub j. When some d sub j is decremented by the removal of d sub j or d sub I. Clean that up. The eraser on this thing no longer works. I gotta manually erase. So d sub I when going from S to S prime, and Balanced generality, S prime to S double prime, triple prime, etc. So let's look at this again. So again, really what we're doing is we're essentially doing the exact same thing. We're taking our original sequence, removing the first value, decrementing the next d sub I values in the sequence. But effectively, when we remove our value of 3 there, it's essentially representing a vertex of degree 3. We make 3 connections to the next 3 vertices in the sequence. Likewise, in S prime, our d sub 1 in this case is going to be just equal to 1. We remove it, add an edge, the next vertex, and we get down to S double prime, which is 0 and 0. We don't have to do anything because we're done. So let's take a look. Just use that same sequence. And here, we could arbitrarily just label these V1, V2, V3, V4, just for visualization purposes. So as we did, we remove value of 3, decrement the next 3. So effectively, we remove V1, we add edges to V2. All the ones that get decremented, V3, V4. And then now we have our V2, V3, V4. Constructor S double prime. 0, 0, moving. So we do that, we're adding an edge from V2 to V3. And look at that. We've realized the graph, which is isomorphic to our original example. Drawn slightly different. Drawn with an edge crossing, if you will, which we'll talk about in great detail later. So somewhat, once you get the basic idea, basic algorithm, I think it's fairly straightforward. So let's work through another example. Why not? Really drive the point home here. Example part 2. Oops. Example 2. Let's go. So we got our S here. We got 5, 5, 2, 2, 2, 2. Looks like that's a even sum of those values in the sequence. So we've checked off a necessary condition for the sequence to in fact be graphic. What about a sufficient condition? Well, let's take a look at S prime here. So we remove -1, -1, -1, -1. 5 times. And probably draw this out too. Might as well just do both. It's going to be a little more involved with the drawing, but I think we can manage. Right, this can already tell that this is going to be a mess. So from V1, we essentially have an edge to all 5 other vertices. Our S prime. 4, 1, 1, 1, 1. All right, how do we get our double prime? Oh, well, boom. 4 times. 1, 2, 3, 4. And our S double prime. This is a bunch of zeros, which is trivially graphic. This represents a graph with no edges. So from our V2, we connect to everything else. There we go. We've realized the graph with the sequence 5, 5, 2, 2, 2, 2. Hamil Hakimi for you. Not too bad. Not too bad. Let's look at, all right. Let's look at some more. Why not? There's a couple other examples that might be useful to recognize. Oh, that's throwing an extra bend. And then 3. What about this? What we got here? I got 6. Got to decrement more than what's this? So it's a sequence of 5 values. We're considering simple undirected graphs. How can that vertex have 6 connections? There's only 4 other vertices in the graph. Again, simple undirected. Can't. So obviously, trivially, that sequence is in fact not graphic. Another example right here. I mean, we could tell right away it doesn't hit the necessary condition of the degrees summing to an even value. But, now let's see what happens if we try anyways. Why not? Give it a go. Okay. Oh, wow. Checks out. Do that. Step 1 complete. Is S prime graphic? Well, we got a degree 1 and degree 0. Obviously, plot graphic. Obviously that can't have because again, we have this relation between S and S prime where S is graphic, S prime is graphic, if S prime is graphic, S is graphic. But since S prime is not graphic, neither is S. Trivially, we can see that S prime is not graphic because there's a center graph with 3 vertices. One vertex having a degree of 1. Simple undirected graph. How would that work? I mean, we'd have just 3 vertices, one of them just edge with no other endpoint. Floating out in space for infinity. That doesn't work. Ill-defined, say. That's so in other words, it's an important thing to recognize. Important thing to recognize is the equivalence between S and S prime in terms of graphicness, graphic realization, realizability, if you will. S can be realized, S prime can be realized. S prime can be realized. So really, for these graph realization things, start with S, then some subsequence, some sequence, not a subsequence, just some sequence that is graphic. But, yep. From projection from the sequence to the graph. So what I was referring to is when I'm saying there's a bijection, what essentially is saying, if we would consider our example here, there exists a map from the value within the sequence to some vertex in the graph in a realized graph having that sequence that has the degree represented by that integer. So it's irrespective of any kind of isomorphic relation. This is only mapping degrees. So we're not like considering the actual structure or topology of the graph being realized, just the degrees of the vertices. Yeah, so like we could, one of these examples, probably not. Yeah, so when we're considering just a non-increasing order, you could easily generate a separate instantiation, a separate realization by just swapping. So here, swapping V2 and V3 really wouldn't do anything because they're just connected to each other, but theoretically, So let's see. I don't think you can generate all possible realizations. You can generate an arbitrarily large number of realizations. I don't know if you can. Let's give it a shot. We got plenty of time today. I don't think that you can generate all possible realizations just by swapping around the order. Don't quote me on that, but I'm fairly certain that you can, because I think I've tried that in the past for various applications. Let's see what happens if we try that here. All right, so we got V1, V2, V3, V4, 5, V6. Let's go with that. All right. And we'd start -1, so we got our V1, our V2. Let's just see without doing anything fancy what happens. 2 S prime equals 2, 2, 2, 1, 1. So you see here we've resorted. So technically we have V4, V5, V6, V2, V3. So here, it's 1 minus 1, so V4 connects to V5 and V6. And then we have just, 1, 1, 1, 1, 5, 6, 2, V3. So we connect 5 and 6. So here's where we could probably differentiate. But again, I don't think it's possible to realize all possible graphs with a given degree sequence by using this approach. So here we could connect, really it'd be V5 to any of 6, 2, or 3, arbitrarily connect that. Or we could just have, in this case, we technically could have generate both instances, but I don't think that extrapolates all possible sequences, all possible. But in this case, yeah, we could generate both using this approach. But again, I don't think that generalizes, but probably don't quote me on that. Fairly, I give it a 65% certainty that it does not generalize. I feel like I would have seen that in practice. Done a lot of stuff with this graph generation kind of stuff. And yeah, for large scale random graph generation, you can use this, but you gotta do some fancy stuff. To actually generate, say, a null model, which is just a random graph, you gotta, with a given degree sequence, you gotta generate a graph that's got a baseline and just do a bunch of swaps. I don't think this will let you. I don't know. Maybe exercise for the students. I'll probably look at it. Just for the sake of knowledge and discovery. That's, it's good exercise. Call it a brain exercise. Brain exercise. And all possible realizations for a given graphic sequence be constructed via above process. Exercise for the professor as well. Okay, let's move it on. Any other questions? Yeah. So this. Yeah, so this case, we were looking at, we could either construct based off how we sorted when we were doing our ordering, we could either construct, what's that? Well, it could be a cycle or 2 cycles in this case. So it could be 2 cycles of length 3. So what we were trying to validate was whether or not we could generate 2 cycles of length 3 or just 1 cycle of length 6. Yeah.
So we have to resort this problem.
Yes.
Okay, then there is 5, 5, 2, 2, 2, 2, 2. So 5, 5 with 2 2s, or with 5. I'm sorry, 5, 5 with 5 2s. You can't generate a graph where both of the 5s are only going to 2s and then.
Yeah, so that's, I think I got what you're saying here. So the answer is no. So here is the graph I believe you were saying. So 5 2s. Yeah, so okay. All right, we already solved our brain exercise. So, oh well, okay, done with that. Good to go.
Sorry.
Yeah, so the reason why we have to like explicitly resort is because that's what was proven. That's kind of the theorem itself, In terms of generation, that's also something, maybe that's another brain exercise. We only cared about generation, could we resort? I think something breaks when you try that. I think I have tried that in the past, but again, only 65% confidence in that estimation there. All right. Okay, any other questions before we actually move on? All right. So let's I think we're gonna start talking directed graphs now. Action notes for today. Nice. So really, it's pretty much a lot of the same concepts that we've already discussed. And the one proof I asked for on the quiz is just proof we've technically already done on directed graphs. Now you're thinking thinking directionally. All right, so what is directed graph? Let's first off, let's give it AKA here. AKA digraphs. So I don't think I've ever defined AKA, so I should probably do that. I was just thinking about that. I say AKA, also known as, in other words, synonym, which is AKA digraphs, also known as. So, and the big takeaway with directed graphs, the big difference obviously is we're now considering directionality. Directionality for every edge. So we got our V, we got our U, we got a VU edge, we got a little arrow. Call that a little arrow, which tells us that edge is in fact direct. So this edge E would equal VU. So the way we write the edge actually becomes somewhat important. What we write, which essentially, when we're considering edge, we write vertex with essentially the edge is coming out of and where that edge is going. So the edge is coming from V going to U. And so we also have like terminology, head and tail for both sides of that edge. Predecessor, successor. You might recognize that terminology from graph mining. Predecessor, ins and the outs, if you will. So, we'll talk a little more differences in terms of adjacency matrix in a second. But that's basically it. We're not considering directionality to the edges. The consequence is for a lot of the stuff we talked about, we have to consider the direction that the edges are going now. So a path, direct path is going to follow edges. Cycle is going to follow the direction of the edges specifically. Walk trail, generally speaking, we're going to be following the direction of the edges. So, hair on there. Right. So walks, let's just write it out. Walks, paths, trails, cycles. Same definition as with undirected. Undirected graphs. But must follow edge direction. Start at the tail, go to the head. Direction. I mean, obviously, here we have a directed path. Directed cycle. And for more examples here, let's consider a simple graph. This is specifically for this case. We'd still consider a digraph to be simple. There's an edge from B to U and an edge from U to V. Those edges are considered separate. Even though there's technically two edges in between U and V, so we're considering directionality. There's only one edge from V to U, one edge from U to V. So it's still a simple graph. I also have the notion of a self loop. And so this not underline the not emphasis. Yeah, because now we have two edges going from U to V, no edges going from V to U. Then considering directionality, not simple graph. What we got? What we got? Let's talk adjacency matrix. Why not? Got some tricks here that we need to discuss. Got our adjacency matrix. One thing, no longer guaranteed. Could be, but it's no longer guaranteed. Be symmetric. And a non-zero at ij applies edge from I to j. So let's look at an example here. We got our A, we got our B, we got our C, we got some stuff there, we got edge there. Now let's make it two edges from A to C. Example purposes. Self loop on C. Why not? Another edge from B to C. So here we have a loopy multi-diagram. Might call it loopy indicating the existence of loops, multi indicating the existence of multi-edges, multiple edges from A to C, readily observed. Let's consider the old adjacency matrix here. It's way messed up. Base. It's not working. Got our A, we got our B, we got our C. A, B, we got our C. So what we got no edges from A to A. We got an edge from A to B. Two edges from A to C. Wow, cool stuff. All right, what we got with B? Nothing from A, nothing to A, nothing to B. Got one to C. C, got nothing to A, nothing to B. It has a self. So here, as you can see in our diagonal, slight difference there, self-loop only counts as 4. And this, a little bit of nuance here. sum of row gives us our out degree, sum of row, or not a row, but a column. All gives us an in degree. So we got some out degrees, we got some in degrees. There's a differentiation here. I don't think we've properly defined this, but the out degree, well, in a second, out degree essentially is the number of edges coming out of a vertex. The in degree is the number of edges pointing to that vertex. So out degree, edges pointing out, in degree, edges pointing in. So here, the adjacency matrix before, sum of the rows equal to sum of columns in our symmetric adjacency matrix for undirected graphs. Here is no longer the case. As we can see, it's very much not symmetric. And here, sum of the in degrees, or in degrees equal to sum of the columns. So if we look at C, 2 in from A, 1 in from B, and 1 in from C via the self loop. Out degrees, sum of the rows. A has 3 edges coming out of it, 1 to B, 2 to C. B has 1 edge, C has 1 edge coming out of it, pointing back to itself. And so out degree, we write D plus D equals the edges, number of edges, coming from the in degree, similarly. Number of edges going into B when we're considering the directionality. Likewise, we have neighborhood notation, out degree, out neighborhood, and minus V. All right, nice. Page. It's all right. All right. So, any questions? That's true. I'll be. Yep. What's that? So that's only the case with undirected graphs. The reason why is we're considering out degree and in degree separate, so both of those are accounted for with just this index via some of the rows and some of the columns. With undirected graphs, we have ourselves a self loop that's technically degree of 2. I mean, so what we have when we're considering C and we're considering a directed graph, technically we're incrementing by 2, but we're incrementing the in degree by 1, out degree by 1. Whereas with undirected graphs, since we don't care, we don't have directionality, it's plus 2 in total, because it's, one edge here, 1 out, 1 in. The other way it's just 1 and 1. That's our adjacency matrix for you. Direct. I guess we already discussed that. Let's just say more directed degrees. There's really no need for a delineation here. Okay, all right. So we have similar notation for the kind of degree stuff that we talked about, minimum, maximum. And so we have little delta, which is max, comma, min, or no, these are just min, out, comma, in, degrees, G. And we have big delta similarly, big delta G, delta, or big delta G minus equals max, out, comma, in, degrees, in G. Just some notational stuff for you. And our degree sum formula. It's a slight difference here. So the sum of the degrees, the out degrees, equal to sum of the in degrees, which is just equal to m. Sum of the in degrees equals sum of the out degrees equals m, which is just the cardinality of the directed edge set in our directed graph. And so it's pretty straightforward why this holds. And each edge contributes exactly +1 to the sums of in and out degrees. So each out degree +1 to the out degree sum. Each edge +1 to the out degree sum +1 to the degree sum. Has to come out of somewhere, has to go into somewhere else. Can't have that edge just pointing out to space. You know, we already said it's ill-defined. We don't do that. Not in this class. I think degrees, recall degree sum formula for undirected graphs is sum of the degrees equal to 2m. Yeah, because we're differentiating between in degrees and out degrees there. So each edge, +1, one side +1 to the other to the same sum of undirected degrees. Yeah, that's kind of why, the self loop and the adjacent matrix, how we consider it, really how we consider it in terms of degrees, is +2 for undirected self loops. For directed graphs, it's just +1 to out degree, +1 to in degree. We're considering each edge, where it's pointing to, where it's pointing from, we consider them different. So, here we go. All right. And similar stuff as we did before. All right, so we have the similar notion of a degree sequence, same but different kind of situation here. So the degree sequence of a directed graph we got to start considering in-out degree pairs that represent some vertex. So if we now consider, say, something like this, our sequence So, vertex, just label these 1, 2, 3, 4. So for vertex 1, in degree is 1, out degree is 1. Vertex 2, also same case, in degree, out degree, 1, 1. Vertex 3, 3, 1. 10, really doesn't matter if it's in comma out or out comma in, as long as it's consistent. And then final one, in degree of 1, out degree of 0. So again, we have a graph realization problem. We aren't going to go into as much detail with directed graphs as we did with undirected graphs. We are going to kind of touch on similar realization problem for potentially loopy multi-diagraphs. Have something a little different. So that's degree sequence for our graph G. Okay, there. How can we tell S is graphic, or digraphic, if you will? Put that down. Digraphic. It isn't proper terminology, but it is in this class. How can we tell if it's, well, necessarily. Necessary condition. Kind of thinking back, kind of formula, etc., etc. Pretty much our old friend degree sum formula. If we sum up the integers, they must equal sum of our out degrees. Classic necessary condition, graph realizability, given a degree sequence. What about sufficiency? About our sufficient? Well, So, really what we're trying to say is if the sum of the vertices 3 equals it is in fact a sufficient condition. Eventually, read this quick. The reason why is because it's another good example of a proof by algorithm. So why not? One of the tools in our bag of tricks. And we got a few tools in that bag so far. Proof by algorithm is a new one. Decided to do this proof because it's a good one for that kind of example. All right, so sufficiency. So this is in fact the sum equal to sum is in fact a sufficient condition. So let's note for only for loopy multi-diagrams. Kind of like what I said before, the sum of the degrees equal to 2n is also a sufficient condition for loopy multi-graphs. So if the degree sum formula holds, you can construct the realization with loops and multi-edges. But it's pretty trivial because you can just start throwing multi-edges. Self-loops is necessary. But yeah, figure just prove this for loopy multi-diagraphs, and really it's kind of the same idea with undirected simple graph, or undirected graphs, not simple, loopy and multi. So how can we prove it? Proof by algorithm. All right, let's go. So, okay. By algorithm. Yeah, it's kind of, I don't know. All right, it's proof by algorithm. So, I mean, when we're doing a proof by algorithm, really, if we're able to create algorithmically a realization of a graph given a sequence that has the property that sum of the integers equals the sum of alpha degrees, then we're pretty much done. You know, get the power of proof by algorithm. So, what we're trying to show again here is that if sum of the integers equals the sum of the alpha degrees over all degree pairs in a sequence, then that is realizable as a looping multiple. So let's consider some arbitrary pair in that sequence, which we will define as d plus sub I minus I, such that I bound below by 1, bound above by n, and obviously m equals sum of the integers, sum of the alpha degrees, just shorthand notation there, as given by our initial assumption. Consider m dots. So this, you know, kind of, I don't know. I don't know. I'm just doing this, saying dots. I'm going to change it in the future, I think, if I do this proof again. Because I think that's confusing to be considering dots when those dots aren't representing vertices in the context of a proof by algorithm for constructing a realization of a graph. I disagree with this terminology, but, you know, sticking to it because that's what we got. So, putting this together at 7 a.m. this morning, and I didn't have a better idea at the time. So, all right. So, what do we have? M dots. D sub I plus dots get labeled I. We'll see what this means in a second. This is also D sub I minus dots get labeled negative I. Now we'll consider our n vertices. The dots, again, are not vertices. They're going to be representing edges. You know, that's, well, we can fix that right now. And, or maybe we can consider m lines. All right. Consider n vertices. Obviously labeled, you know, 1 through n, v sub 1, oops, no, v sub I, v sub I, v sub n. For each line, not dot, construct edge from positive label to negative. Via vertex. So, this is essentially our algorithm. Construct a realization of a loopy multi-digraph. So again, proof by algorithm, considering some arbitrary degree sequence consisting of pairs of in and out degrees. Each of those represents the in and out degree of some specific vertex I. We have our M lines, which we will have labeled. So again, the sum of the out degrees equals M, sum of the in degrees equals N. So each line gets labeled uniquely with some I. Each line also gets labeled uniquely with some negative I, meaning we have kind of a bijective mapping from in degrees in a sequence to a line, out degrees in a sequence to a line. So the same line can in fact get labeled with both for some arbitrary I, and negative I. That would just represent a self loop in that case. But each line should only have one specific positive label, one specific negative label. Then we consider our n vertices, and for each line, we essentially use those vertices to construct an edge. So that line gets transformed into an edge. Wild stuff. All right, let's look at an example here. So we have sequence 1, 3, 1, 2, 3, 1, 1, 0. So sum of the out degrees. Let's for this case, let's say out in, switch it up, because why not? That's how I have it drawn. So that's how it's going to be. In this specific case, again, it's pretty arbitrary if you list out or in first. I don't think there's any formal, reason to do it one way or the other. Yeah. So out, list the first. So sum of the out degrees, 1 plus 1 plus 3 plus 1 equals 6. Sum of the degrees, 2 plus 1 plus 0 also equals 6. We checked our necessary condition. This is in fact realizable as a loopy multi-diagram. All right, but let's draw our lines, all 6 of them, 2, 3, 4, 5, 6. We have our vertex labels, so our I's, I equals 1, 2, 3, 4. So positive labels for out degrees. We're going to label one line with 1. And I label one line with 2. 3 lines with 3. 1 line with in degree. -1, -1, -1, 3 times. -2, -2, and negative. Now we direct our lines. What do you know? We have an edge list now. Look at that. There's our edge list for our loopy multi-digraph that we've realized. Well, we haven't realized it yet, I guess. I don't know. Depends on how you define it. We haven't drawn it. Technically realized the edge list for it. 1, 2, 3, 4. So 1 to 1, 2 to 1, 3 to 1, 3 to 2, another 3 to 2. Wild stuff. Nice. Realize the graph. Directed edges. Amazing. Okay. So this is pretty straightforward, I'd say. Really just, proof by algorithm here. I mean, I'm going to ask you to do it on the quiz. Note that I did update the quiz as of 7 a.m. this morning. So if you looked at it last night and if you did it already, you could just submit it, and that's fine. You don't have to redo it. But I made the directed graph realization problem a little easier. Because originally M was like 14 or 15, so I was like writing down the solution, going through it. I was like, yeah, that's a pain. I'm not gonna make them do that. So I made it easier. So if you already did it, then I apologize. But it's easier now, so it's more straightforward. It's really just applying this and showing it can be realized, and then you're done. So one more thing I wanted to talk about here. One final thing. Not in too much detail, but kind of going with the theme of same but different situations. So Eulerian. So a digraph is Eulerian if and only if there exists closed trail on that digraph containing all edges. So Eulerian digraph is digraph with closed trail. Exact same definition as our in the undirected case, except now we're saying digraph instead of graph. Obviously, the trail in this case is a trail that follows the directionality of all edges. And so how do we prove the existence of a trail? Well, really, you do it the exact same way. I was thinking that would make for a good question on an exam. Make you do that. Kind of like I did on the quiz with the second question, the second proof. It's the exact same thing we already did with undirected graphs. See who's paying attention. That's what we like to do. All right, so we're at the stopping time. So really, it's quiz time unless there's any questions. So, yep.
So can you go back up to the example?
This guy?
Yeah, how did you get the negative numbers on the bottom?
So the positives correspond to out degree. So for vertex 1, it has an out degree of 1, goes there. In degree of 3. So we label 3 lines with that, and likewise for 2. 2, 1, 2, 3, you know, et cetera, et cetera. Does that make sense? So the negatives correspond to the in degrees. Positives correspond to the out degrees. Any other questions? Yep. I do not know. Like muted. I wonder if I've been muted this whole time. I think it's just the speakers. Okay. Yeah. Any other questions / jokes? Okay. I'll stick around for the next whatever. Just put this up. We can work on it and some questions.
Quick question. I know your lessons, but when you talk about this, I'm so confused about it. If I want to transfer this to math class, well, the pop said I could do it on the SIS.
So yeah, you can't, as of this semester, as close as possible. I can make it so I can do like manual overrides. So just send me an email, your RIN, it'll probably be easiest. I'll just do that for you. Okay, good. Thank you. So I'm still here. Yeah, it has a self loop, it's still digraph. I mean, digraphic isn't a real term. You have to worry about it. Yeah, I'm just gonna shut it down now. If you have any questions,
Oh.